Welcome to my presentation on one of the greatest minds in history, Carl Friedrich Gauss, often referred to as the Prince of Mathematicians. Today we will explore his life, groundbreaking contribution, and how his work continues to shape mathematics and science. Before diving into his contribution, let's briefly reflect on why Carl Friedrich Gauss is revered. A German mathematician and physicist, Gauss was born in 1777 and showed exceptional genius from a very young age. His work spans pure and applied mathematics, physics, and even technology, making him truly a polymath. Gauss's genius was recognized early, and he was supported by the Duke of Brunswick to pursue his education. Among his many accomplishments, he proved the fundamental theorem of algebra in his doctoral thesis in 1797. He also wrote the Disquisition Arithmeticae, a seminal work in number theory. Additionally, Gauss invented the first electromechanical telegraph, bridging mathematics with practical sciences. His title, Prince of Mathematicians, is a testament of his lasting influence. Gauss made significant contribution to mathematics and physics, with notable achievements in the least square method, the Gaussian distribution, and the differential geometry. So let's start by understanding the normal distribution. One of the Gauss's most recognized contribution is the Gaussian distribution, also known as the normal distribution. This bell-shaped curve is fundamental in probability and statistics. Defined by the mean, which determines the center, and standard deviation, which defines its spread, this distribution is central to data analysis, hypothesis testing, and machine learning. The Gaussian distribution's shape depends on its parameters. Changes in the mean shift the curve's center, changes in the standard deviation stretch or squeeze the curve. This flexibility makes the Gaussian distribution crucial for modeling real-world phenomena. A key property of Gaussian distribution is the 68, 95, 99% rule, also known as the empirical rule. It says that 68% of the data lies within the 1 standard deviation of the mean, the 95% data within the 2 standard deviations, and 99.7% data within the 3 standard deviations. This helps us understand the likelihood of events and identify outliers which are rare. Data points like the extreme market returns during the COVID-19 pandemic. Over here, as we can see, I have highlighted the COVID-19 returns over the, when there was stock market crash during the COVID-19 period. And as we can see, the returns are considered to be an anomaly since they lie beyond the 3 standard deviations. The Gaussian distribution is foundational in machine learning. For instance, we applied Gaussian naive Bayes algorithm to the iris dataset. Assuming the features follow a Gaussian distribution, the model achieved an impressive 98% accuracy in classifying the iris species, and it actually made only one error in predicting. The broader impact of the Gaussian distribution is the Gaussian distribution influences diverse fields such as hypothesis testing, Bayesian statistics, machine learning, computer vision, quantum computing, and natural sciences like neurobiology and cosmology. It is a cornerstone of modern computational and natural sciences. Now let's move on to his next work, which is the least square method. Gauss also developed the least square method, a technique for finding the best fitting curve or line by minimizing the sum of square differences between the observed and predicted values. He first applied this to predict the celestial body positions, and today it is used in regression analysis and machine learning. The core idea of the least square method is to minimize the sum of squared residuals, where residuals represent the difference between the observed and the predicted data points. In linear regression, for instance, this method determines the optimal slope and the intercept of the line. Over here we can see I have applied least square regression line, and we can see plots from a randomly data generator from a random data generation, The red line is the least square fit line, and the dots are the observed data. And over on the right side, you can see the residual plot, which is the difference between the predicted and the actual value. And overall, it's an optimization technique. So its motto or its aim is to minimize the sum of squared residuals and to find the best fitting line. The least square method is widely used in linear regression, polynomial regression, and the time series analysis. Now moving on to his work in differential geometry. Gauss's contribution to differential geometry were revolutionary. His work in this field laid the foundation for modern geometry and influenced physics, engineering, and mathematics. One of his most famous results is the theorema egregium, which we'll discuss next. The theorema egregium states that Gaussian curvature is an intrinsic property of a surface, which means it depends on measurements within the surface, such as the distances and the angles. It's independent of how the surface bends in three-dimensional space. This insight bridged intrinsic and extrinsic geometry. Mathematically, the theorem relates the first fundamental form encoding intrinsic geometry and the second fundamental form describing how the surface curves in 3D. Gauss showed that Gaussian curvature derived from these forms is entirely intrinsic. This finding has applications in physics and computer graphics. As you can see over here, the first fundamental form and the second fundamental form, and the principle, and like the Gaussian curvature can be given by the product of the principal curvatures, which are the maximum and minimum curvatures at point on the surface taken in the orthogonal directions. And here is one of the visualization which we took for the Gaussian curvature. As you can see over here, we have a hyperbolic paraboloid surface, and this is the heat map which depicts the Gaussian curvature value at each point. So now let's see the broader contributions beyond the Gaussian distribution, least square method, and the differential geometry of Dr. Gauss. So one of them is the Gaussian Markov theory, the orbital mechanics, law of magnetism, quadratic reciprocative law, the maximum likelihood estimation, which he didn't exactly derive, but he obviously laid the foundations for bringing up with this theory. The fundamental theorem of algebra, as we have discussed, he did prove, and he did provide some of his work for it in his doctoral thesis, the differential geometry, as we have discussed, and in the field of optics as well, and geodesy and surveying, where he used his findings of the differential geometry in better mapping and bring up better maps of the Earth. To conclude, Carl Friedrich Gauss's contribution to mathematics, science, and technology are unparalleled. His work in probability regression and geometry laid the groundwork for many modern advancements. Thank you for your time, and I'm happy to answer any questions.